Okay, let's look at just a couple more properties of integration. Um, these are also pretty natural if you just draw some pictures. So the first one is, well, what happens? Is there some nice bounds we can have? So like, like a lower bound, upper bound, like, can I say for some reason, my integral is between, if I draw some picture that like the integral is between 3 and 10 or something, can I find a number that bounds it from below and it bounds from above? So let's just imagine we have some function. Let's say it looks like, I don't know, this or something, right? So here's my function. Like, actually, let me draw it slightly differently. Let me put this down here. Okay, and let's make our interval, from A to B, something like that. So this is the area where we care about right here, right? And I guess the question is, I claim that there's some actually pretty easy bounds that you can see. So first thing to notice is like, there's a maximum value the function reaches on this interval, and there's a minimum value down here, right? So there's a minimum value it reaches. And so, I don't know, the books tend to call this little m and this big M for maximum, little m for minimum. And what you can sort of immediately see is like, okay, the area that we care about is the blue area, the integral from A to B of f of x dx. And it's like 0 down here. But there's a couple rectangles, right? Like there's a rectangle right here, for example. You can zoom in if you like. There's this rectangle. And clearly the area is bigger than that, right? The area under the curve is bigger than that. So that's greater than the area of the yellow rectangle. And then there's some bounding, there's some other big rectangle. Let me use orange, I guess. There's this big rectangle right here. And then it's sort of clearly, the area under the curve is less than the area of the orange rectangle. So of the orange rectangle. Okay, so then what is the area of the yellow rectangle? Well, the base is b minus a, right? And the height is little m. So we can really just say here, m, little m times b minus a, well, that's less than, I guess there could be like equal, if the function was constant and the max and min were, if little m equaled big M, I guess you should have less than or equal to here. That integral, which is less than or equal to, and then, right, well, the big rectangle, still base b minus a, but now the height is m, right? So that's big M times b minus a. So I guess I should probably say if f of x is between little m and big M on the interval from A to B. By the way, that's a notation for A less than or equal to x less than or equal to b, the square, the rectangular, the square brackets, A comma B. Remember, that's less than or equal to. If it's less than, you use parentheses instead. So if that's true, then this this formula right here is true. And so if you know something about your function, like, for example, say it's going up the whole time on the whole interval, not like the picture I have here, but say it was something where it was actually going up the whole time. Well, then the lowest point would be the first point. So you could just plug A into the function to find little m. And then you could plug B in to find big M. And then you could actually compute these pretty easily, and that would give you numerical bounds on the integral. Okay, so that's pretty clear. That one's not too bad, I hope. And then the second one that's also not too bad is just if I want to compare two integrals, well, let me draw another picture. Let's just say I have a function like this, and I have another function, say like this. So this is, let's call this f of x. Let's call this g of x. And let's have our intervals again, say from, oh man, that is not what I wanted to happen. From A to B. And notice I even have this, these dipping below the x-axis. It's actually not going to really matter. But I think just clearly like thinking about Riemann sums, thinking about anything with areas, and thinking about signed areas, it's going to be pretty clear that, the area under f of x, which is kind of like this, because there's some positive area here, some positive area here, a little bit of negative area there, is going to be bigger than the area under g of x, which has some positive area there, and then a bunch of negative area there. So you can just sort of say pretty quickly, if f of x is greater than or equal to g of x on the whole interval from a to b, then the integral from a to b of f of x is greater than or equal to the integral from a to b of g of x. So if the function's higher, then the integral's higher also. By the way, it's good that the areas are signed areas then, because, right, if it's the area between the graph and the x-axis, then that, it's not clear. Like if we considered, if we consider this area down here positive, it's not really clear what's bigger between this and these two. But so it's actually nice. It makes a lot of these properties more nicer to the fact that the area is a signed area. It's positive and negative areas. Okay. So that's it. I think I'll stop that one there.